Hi everyone, and welcome to another one of my videos. The topic of this video is elimination reactions. More specifically, exactly why is it during some elimination reactions you can get two products, whereas in other ones there's only a single organic product. An elimination reaction will involve atoms being removed from two adjacent carbon atoms and a double bond forms between them, so an alkene functional group forms. And the reasons why two products can form instead of one essentially comes down to this. For starters, the carbon atom that is bonded to the functional group being removed, that could be a halogen or a OH, it must have more than one adjacent carbon atom with hydrogens attached to it. If we were to have a look at some models, this will be an example where the requirement is not being met. The carbon that has the OH attached to it only has one direct carbon neighbour. This would be propan-1-ol or 1-propanol. What that means is that when a double bond forms, it is going to have to form between those two carbons right there, where the H and the OH are removed, because there's no other neighbouring carbons to this one. There's no other possible places for the double bond to form. Okay, trying to form a bond between this carbon and a distant one to form some sort of cyclic structure is really out of the question. It's not what will happen in the elimination reaction. It is only going to be between two neighbouring carbons. If you have only two carbons that could possibly be involved with that, then obviously there's only one place for a double bond to form. If there are more than one adjacent carbon atoms to the one carrying the relevant functional group, there's one further step in the picture. And that is that those adjacent carbons, neighbouring carbons, must be different to each other in terms of the groups that are attached to them. Here's an example where that rule is not met. We've now got an OH in the middle of the chain, and there is an adjacent carbon on one side and there's an adjacent one on the other side, which means there's an opportunity for a double bond to go on this side or to go on that side when the groups are removed from each of those atoms. However, this carbon here has got three hydrogens attached to it, and this one here has got the exact same setup of three hydrogens attached to it. So it does not meet that requirement. Slight modification, however, to butan-2-ol or 2-butanol. We still have two neighbouring carbons, being this one and this one. This carbon further down the chain is more or less irrelevant to us. However, the presence of this means that this carbon is now no longer identical to this one, because this one has a methyl in addition to two H's as opposed to just three H's. What that means is that if a double bond was to form across here, it's going to end up with a different outcome as opposed to when it forms across there. So let's have a look at a couple of those examples actually happening. So this is an example where there's only one possible organic product, and if we have a go at using the models, hopefully they might help illustrate that regardless of which adjacent carbon takes part in the reaction, the end result is going to be exactly the same. So, looking at the models, I have two copies of our starting organic molecule. There are adjacent carbons, however those adjacent carbons have identical groups attached to them, which means that if the OH is removed along with one of these H's, and it actually makes no difference which one I take, because with rotating single bonds they're all equivalent to each other, but if a double bond forms to the left side, I end up with that. If a double bond forms to the right side, this, and really what we're looking at here is two copies of the exact same thing, because this structure flipped over is actually the same as this one. No matter which adjacent carbon was involved in this reaction, the double bond always ended up on the end of this chain. Propene is the only possible product. A single organic product is formed. And now an example where two products will form. We're now dealing with the starting molecule of butan-2-ol or 2-butanol, and I'm just going to reconstruct a couple of structures here. The important thing here is that we do have adjacent carbons, there are two of them, but they are now different from each other. And what that means is that when I remove a hydrogen from either carbon number 1 or carbon number 3 and form a double bond to that carbon, there is going to be a different outcome in terms of the structure of the molecule. And let's see if the models can maybe help us out with that. So, to make these look more or less the same, two examples of butan-2-ol, and the double bond is either going to go across to the terminal carbon right there, or it's going to go across on the left side across there. It's possibly reasonably obvious that getting a double bond on the end of 4 carbons in a row is going to be a different structure to getting a double bond in the middle of a 4 carbon structure. I've happened to build the cis version of this. Cis and trans as products of reactions more or less produce in equal amounts. It's not important. The key thing here is I've made one structure where it is but1-ene. Double bond is attached to the first carbon in the chain. However, if I react with the other adjacent carbon, I now get but2-ene, where the double bond is between carbons 2 and 3 in the chain. So there are 2 products in this reaction. The reason why there are 2 products, if we were to just go back to the screen, that because the adjacent carbon atoms were different from each other, we will get 2 different products depending on which one of those will lose the H atom and gain a double bond.